this is that. Today we'll now be doing question 4 of 2009. Now we have something. What's this something? It's a parabola and a line. So what do? We have a line which is called a normal, which means it's perpendicular. And you think about it, it's perfectly normal for it. I love my puns. So by differentiating, we know that the gradient is 2a, so that's right, d over dx at a equals to 2a. And the normal has gradient minus 1 over m, and m has 2a, so it's minus 1 over 2a. Because then you go check it on Desmos or any other graphing program, and you can just play around with it. Minus 1 over m is always perpendicular. Got that? Hence, the line L has equation y equals to minus x over 2a plus c. But wait, there's more. We haven't found c yet. So a squared equals to minus half plus c. c equals to a squared plus half. So this means that y equals to minus x over 2a plus a squared plus half. There. Or, as the MAT would love to put it, y minus a squared equals to minus 1 over 2a x minus a. So, for what values of a does L pass through P? So, let's substitute y equals to 1 and x equals to 0. So, 1 minus a squared equals to half. So, a squared equals to half. So, a equals to plus or minus the square root of 2 over 2. Or you don't like our denominators rationalized, you can have plus minus 1 over the square root of 2. Either way is fine. I like my denominators rationalized, but it's up to you. So, determine QP squared as a function of a, where QP denotes the distance from P to Q. So, let's write this. P equals to a squared, and Q is 0, 1. There. So, this means that the Euclidean distance, mod QP squared, equals to a squared plus a squared minus 1 squared, which you can go expand it, becomes a4 minus a squared plus 1. There. So this can be differentiated to get 4a cubed. So let's write d over dA equals to 4a cubed minus 2a equals to 0. So this means a squared equals to half. Again. There we go. A equals to plus or minus the square root of 2 over 2. But don't forget, we also factorized an a into it, so we threw an a away. But wait, this a has the power to become 0. So it can also become 0 as well, turning the whole expression into 0. So, though 0 is a local maximum, those were the three values determined last part. Or by completing the square, you could complete the square, but it's up to an exercise for the person who's watching it. Find a point R in the xy plane but not on C, such that RQ is smallest for a unique value of A. So this means we need to find a point R such that RQ is smallest for a unique value of A. There are many points where this is the case, but we're only asked to find one for each point. Let's try R equals to 0 minus 1. And it's relatively easy to also justify it to become 0, 0. In general, it could have 0, A, or basically anything. So, C is distance 1 away, no other. So, for 0, 0, C is distance 1 away, no other point in the upper half plane, as it's called in the theory of modular forms. You could check summing it up by after Ashley Robert goes scoreboard complex definition of the upper half plane. C, once one there, it also involves complex numbers. So no other point in the upper half plane, and hence no other point on C is as close as 0, 0. The same argument can be used for any point on the negative y-axis. And we're done.